Hi, students. Okay, let's resume lectures on chapter 3. So last time we were considering Fourier transform, properties of Fourier transform. Specific to Fourier transform. Specific to Fourier transform. So today I'm going to finish this with some more important properties. And which is as follows. First, a reminder that Fourier transform of x of n is x of omega equals the sum of x of n e to the minus j omega n, which is the z transform, where z is replaced by e to the j omega. So more properties about this. Assume now that x of n is real. The danger is to say that x of omega is real. I mean, this is typically the type of mistake I hear. But obviously, if x of n is real and this is not real, then there's no reason for the whole thing to be real. In fact, the only thing that can be said is the following, is that if you calculate x of minus omega, you get x of omega conjugate. And this is, in fact, equivalent. Now, this type of property is something you've never seen before. But imagine this equality without the conjugate. Suppose that x of omega satisfies this equality without the conjugate. What would be the name for this property? Can somebody tell me? Suppose that this is satisfied without the complex conjugate. What would be the name of this property? Can somebody tell me?
Inverse.
No, time reversal is not the property, it's a transformation. And here it's not time, this is frequency. Suppose you had this equality without the conjugate. What property x of omega would be? Nah, there's no time here, it's frequency. X of omega is a function of omega, and assume that it satisfies this equality without the complex conjugate. Okay, somebody choose symmetry. What type of symmetry? Without conjugate, without the conjugate. Suppose you have this without the conjugate. Even. Yes, even. All right. Now, so if there was no conjugate, this would be called an even function. Now, because of this conjugate, then somebody knew the answer. It's called Hermitian symmetry. So this function is called Hermitian symmetric. Hermitian symmetric. Hermitian from Mr. Hermite, original pronunciation, Mr. Hermite. He actually was alumni of my own school, probably 2 or 3 centuries ago. Actually, to tell you the truth, even Fourier was an alumni of my school. Either alumni or professor, I forgot. One of the. All right. Now, proof. You want to go to that school? Okay, let me tell you, it's not easy. Okay. Proof. I'm going to prove the just one part implication. So assume x of n is real. All right, assume that. Now, what is x of minus omega? That's easy. You take x of omega and you replace this by minus omega. Then you replace this by minus omega. All right. Now, I'm sure everybody agrees that this can be written as e to the minus j omega n conjugate, right? Meanwhile, can I write that this is x of n conjugate? Can I write this? Why? Why can I write this?
Because it's real.
Yes. All right, now we have this, again, A conjugate times B conjugate is AB conjugate. A conjugate plus B conjugate equals A plus B conjugate. So in the end, this is equal to this conjugate, and then applying these properties, I get that this is the whole thing conjugate, which is x of omega conjugate. Right? So I have proved this implication. Now the other implication, next, done. I like this technique of proving DIY. Okay, now a mistake. I'm going to write a typical mistake. A typical mistake of students. Is to say if x of n is real, then x of omega is real. Okay, if you make that mistake, you get shot right away. There's no reason for this to be true. All right. Next property. You remember I mentioned to you that Fourier transform has the property of duality, which means that the inverse Fourier transform is similar to the Fourier transform. So suppose that we assume, instead of assuming x of n real, assume that in the Fourier domain x of omega is real. Then it's easy to expect that x of minus n is x of n conjugate. It's a simple consequence of the duality of Fourier transform. We get Hermitian symmetry in the time domain. All right? I'm not going to prove it's similar. Now, the next property is very easy to understand. I'm going to assume, okay, don't write for now. What I'm going to do, I'm going to assume that we have both these two properties in the time domain. So if I assume we have both of these properties, obviously we are going to have these two properties, right? So this is a trivial consequence. Okay, so no problem. That is easy to understand. But now it's obvious that since x of n here is assumed to be real, there's no need to put complex conjugate, right? I can remove it. We are saying the same thing, right? Same thing here. Since we assume x of omega real, I don't need to put the conjugate here. Okay, so we have also the equivalence between these two. Now, can somebody tell me a much shorter way to express these two properties? X of n, instead of writing this, can you phrase this in a much shorter way?
X hat of n.
Say it again.
I said X hat of n, the X with the line on top with the n.
X hat?
Yeah, I'm not sure. I don't remember the name of it, but it's the X with the line on top of it and then n.
No, okay. The real answer, the good answer is from Veronica. She said real and even. That's it. So saying this is the same as saying this, which is also the same as saying that. And same thing here. We say x over omega, even and real is the same thing. All right, so we come from what we had before, that if x of n is real and even, then x of omega is even and real. On purpose, I write even and real in this order, so that you understand that the even comes from real, the even comes from real, but not you don't have x of n real equivalent to x omega real, according to the mistake I mentioned. All right, so this is different. All right, now the next property is only for information, okay? But curiosity, I'm going to assume the following: x of n real and odd. I'm going to ask to give me a wild guess, just a wild guess, no shooting, wild guess about what you expect x of omega to satisfy. Just give me wild guess. It looks like you saw the book, right? You saw the book. Shahana, you want to say? The answer I got, it looks like it's from somebody who saw the note of the book beforehand. All right, so you saw it. So the answer is odd and imaginary. I'm not going to prove it. You can prove it yourself. The reason I'm showing that to you is that it could be that x of n real, be real, and not only x of omega is not real, but it's worse than that, it's purely imaginary. Just to emphasize that saying x of n real is x of omega real can be completely wrong. All right. So this completes the properties of Fourier transform. Now I would like to go to the next paragraph, which is called frequency, magnitude, and phase response of LTI system. So consider an LTI system. H of n is the impulse response. The Fourier transform of H of n is called frequency response. Its magnitude is called magnitude response. Angle is called phase response. So why these ones are important? We saw that first that if you put that's the fundamental formula. If you input a pure complex exponential sequence, you get the same thing at the output times a scaling factor, which is a frequency response at omega naught. And if you input a sinusoidal input, oh yeah, I forgot, it has to be a real in this case, then you know that the response is the magnitude response at omega naught, A naught cosine of omega naught n plus theta naught plus phase response at omega naught. Now, suppose that the frequency response is 0 at omega naught. Then the output equals 0. So we say that the input is cancelled, but sometimes you may see the term blocked. But you can imagine many other terminology filtered out. That is another term. Or I don't know, you may eliminate it. Maybe that's less professional term, but we understand. Oh, I was asking for student suggestion, and I put one in parentheses. But or you can invent your term anytime you want. But what is important is to understand that it is sufficient for just a scaling factor to be 0 for the whole output to be 0, whether you are here or if magnitude of h over omega naught is less than 1, then we say that output, the input is attenuated in amplitude if, on the contrary, it's larger than 1, then what do you say? What do you say? What do you say here? Tell me. Amplified. Amplified. Wow, amplified. It sounds like I'm teaching electrical engineering here, right? For the first time. Yeah, I agree with you. If h over omega naught equals 1, then output equals input, right? I mean, yeah, actually, in both cases, in both cases, because if this is 1, then this is 1, but then this is 1 and this is 0. So we say input is preserved. Now, if h omega naught is 1 in magnitude, then we say that input is preserved in amplitude. The reason I'm doing this is just that by analyzing these functions, then you understand what happens to this input, either complex exponential or sinusoid. You see, by knowing the magnitude here, you see how the amplitude has been modified. It gives you physical insight about what happens to the input. Now, properties. We know that frequency response is 2 pi periodic. So obviously, both the magnitude response and the phase response are 2 pi periodic. Next, assume h of n is real. Then h of omega is Hermitian symmetric. Okay, so we just saw it. Now, what can we say about magnitude? obviously the magnitude of this is equal to the magnitude of this. And the phase, the angle, is equal to the angle. Now, all right, so what do we have here? Somebody? Yes. Yes. Okay, more difficult. What do we have here? Oh, you are silent now. Oh, you are silent. Yes. Yes, correct. I mean, if you don't know this, at least look, see what happens on the graph. Suppose this is complex number A. Where do you see the magnitude? It's the length of that stick, right? Where do you see the angle? You have it here. But where is A conjugate? It's here. So what is the magnitude? It is here. What is the angle? It is here. It's clear the magnitudes are equal and the angles are opposite. Everything is graphical. No mystery. So here I can say this is the magnitude of h over omega because I'm using the first equality. And here I'm using the second equality, angle minus angle of h over omega. All right, so then what property is satisfied by magnitude of h over omega? When you take this function at minus omega, you get the same thing at omega. So what name is that? Even, yes. Even. Now, what can you say about this function? Yes, bravo. Hey, it's always the same two who give good answers. Hey, the other ones. Okay, these are important properties. All right, so now we're going to do an exercise. Magnitude and phase response of the following system. Simple FIR system. Sorry. All right, so what All right, so what is the impulse response of this system? It's h of n, which is, so I call it h of n. It is so it's an FIR system. You have 1 here, you have 0 here, you have 1. What is a free, let's say, what is a transfer function? H of z is 1 plus z to the minus 2. What is the frequency response? H of omega is this, where z is replaced by e to the j omega. Now, what is magnitude and phase response? So you remember that h of omega is expressed in terms of its magnitude and its angle using this expression, where h of omega is real non-negative and angle h of omega is real, but typically we assume between minus pi and pi. So to find magnitude and phase, you must find an expression of that type with these characteristics. Now, here's a trick. You see, this has the form of 1 plus e to the j theta. There's a trick to decompose this in this form. You can factor out e to the j theta over 2. If you expand this, re-expand this times this gives you 1, and this times this gives you. But what do you recognize? What do you recognize here? What is it? It's equal to somebody? Yes. Yes, 2 cosine. 1, no, 2 cosine, yes. 1, 2 cosine. So I would like to write 2 cosine theta over 2 e to the j theta over 2. Now look, looks like that, right? This looks like that. So it looks like this is the magnitude and this is the angle. Yes and no. But wait. I'm not done. So I'm not done yet because this is omega. All right. So take theta equals minus 2 omega. Replace theta by minus 2 omega. You will get this, right? So by doing so, h of omega is equal to this. Is going to give you 2 cosine of minus 2 omega divided by 2, which is minus omega, but it's also omega because cosine is even. E to the theta over 2 minus, so it's a minus j omega. Okay, so we have this. And you compare with this. And then you say, oh, we are done. This is magnitude of h omega, and minus omega is the angle. Do you think it's right? No. No, it's not right. Why? Because we don't know if this is positive. What if this is negative? All right, so we can discuss. If cosine of omega is non-negative, then yes, this is the magnitude, and the angle is minus omega. But what if cosine of omega is negative? You cannot say that. You cannot write this, because then you write something positive equals something negative, and then you get shot. No, actually, you don't get shot. You commit suicide. All right. So how do we solve this? I'm going to cheat. I don't like this because it's negative. So you know what? I'm going to make it positive. No, yeah, too easy. You cannot do that, right? However, you can do this. It's allowed, right? But I don't like this because it doesn't. You want to have this form, right? You want to achieve this form, e to the j something. But look, do you agree I can rewrite this as e to the j minus omega plus pi? You agree with this? You know, when you add pi, you change the sign. So this is equal to this. This is non-negative. So this time, yes. This time you can write this. All right, so I'm going to summarize so summary. For each of these two functions, you have two cases. Where cosine of omega is positive, this one is 2 cosine of omega. When cosine is non-negative, and then minus 2 cosine of omega when cosine of omega is negative. and the other one is minus omega and minus omega plus pi. Okay? But, remark, look at this. You take this magnitude of h of omega equals this when cosine is positive, and minus this when the cosine is negative. So that means you either this is this when it's positive, and when this is not positive, you make it positive. So isn't there a shorter way to write this? It's just this. But this could be obtained directly from that expression. Because that expression implies what? It implies that the magnitude is absolute value of this times absolute value of this. But, I'm sorry, magnitude. But what is the magnitude of this number, which is on the unit circle, is 1. So you get this right away. Okay? There was no need to do this complicated thing. All right? Now I'm ready to plot. I want to plot this function. And I hate plotting cosine on a tablet. So I'm going to cheat. I'm going to copy the plot from previous lecture. The plot of cosine. All right, so this is the plot of cosine. No mystery, you know. Looks like that. Now, magnitude of h of omega is 2 times this in its absolute value, so no surprise either for the results. You're going to get this. All right. So you flip the negative part, and you get this. Now remember, we only need to plot the function between minus pi and pi because the function is 2 pi periodic. So there's no necessity to plot it beyond. The question is, you remember we expect to obtain an even function. Is it even? Is it? Okay, 6 answers. 11. 16 answers. 17 answers, 18, 19 answers. That's it. Okay, 20 answers. All right. Hey, some people said no. Of course it's even. Look. Even when the graph is symmetric about the y-axis. So it's good. If it was not, then we wouldn't know. We wouldn't, I mean, we would know actually that the result is incorrect. So this will tell you that there's a mistake. Now I want to plot phase response. Okay, so phase response, I'm copying and paste the expression. Now, I will need to plot different different curves for positive cosine and negative cosine. So I will need to, I will depend on this graph. So this is the reason I will need to perform some extension of these values. Did you notice I'm very good at plotting something vertical? It's like perfect vertical, right? All right, so let's plot the axis. So I'm going to plot in the graph in blue. Okay, so when cosine is positive, so that means between minus pi over 2 and pi over 2, I get this straight line, which is easy to plot. It's going to be, okay, the curve minus omega is like that. Okay, so this is minus omega. But magnitude of the phase response is minus omega only in between minus pi over 2 and pi over 2. So I'm going to highlight in blue the correct part. All right, so I'm done with this part. What about this part? This part requires that we plot the different curve, which is this one plus pi. So to get, I need to get pi. All right, so this is minus pi, so this is pi. So minus omega plus pi is this curve shifted by pi. Minus omega plus pi. All right, so the result is going to be All right. Now the question is that we know that phase response must be odd. So is it odd? Do we get something odd? Six, 7, 8, 10 response, 11, 17, 18. Okay, two more. 19. Hey, one more. Okay, 20. All right, so I give you the answer. So some say yes, some say no. Wait a minute. How do you see odd property from the graph? What symmetry do you expect? What kind of symmetry do you expect? Yes, about 0. Yes. No, not vertical. Yes, about 0. Symmetry about the point 0. This part is odd. But what is the symmetry of this point? It's here. The symmetry of this point is here. This is not odd. It's really odd because it's not odd. 2 pi down. Yes, right. Okay, so this can be modified by plus minus 2 pi. Yes, so suggested by forgot your name. The answer is still correct if you move this by 2 pi down. So this segment is shifted by 2 pi. And now everything is between minus pi and pi. You see? Oh, I forgot to say, so reminder, you want magnitude or phase response to be between minus pi and pi. So this part was above pi. These are between minus pi and pi. So these were correct. Now you can always modify the magnitude ratio omega by plus minus 2 pi. So you put this back into the interval minus pi pi. Okay? All right. Question. Is that odd? The new result. Is the new result odd? Okay, 8, 9, 10. 12 answers. 15. 17. 18. Two more. 18 answers. 2 more. 19, 20. Okay. So 6 said no. The answer, yes, it's odd. It is odd. Hey, those who don't agree, I mean, yeah. It is odd. All right, this is symmetric about this. So it's fine. Now, the last item I would like to cover today is y is Fourier transform 2-pi periodic. I mean, we saw it. We know why mathematically, but physically, why do we have this 2-pi periodicity? All right, we saw that if you add 2-pi to a frequency, you get the same thing. Okay, because e to the j 2-pi n equals 1 for any integer n. So something is odd here. Okay, odd. Different meaning. Look, in continuous time, actually, before that, it will be. I'm going to show you a demo in with real signals. So obviously, I will have to show cosines or sinusoids. So what you see with exponential, you see with cosine. If you take frequency omega 1 larger than omega 0, you know that in continuous time, this I mean, take them positive here. Or yeah, you take them positive, all right? You know that this sinusoid will oscillate faster than this one, no matter what. No matter what. So they will be different. We know that. But in discrete time, if you take omega 1 equals omega naught plus k2 pi, you know that cosine of omega 1 n still gives you the same thing as cosine of omega naught n. Isn't that strange? Isn't that strange? All right. I'm going to give you a demo. I'm going to show you a demo. It's demo 1. You have seen in Blackboard there's a section of demo. Make sure to put your display in full screen mode until you see the red line. Okay, make sure that you see the red line that I'm pointing here. So what am I showing? I'm showing in okay, I don't see my cursor. Okay, wait, I'm going to use this. To do this, yeah, you get this. In red, I'm plotting cosine of omega 0 t. Now you say, you don't see a sinusoid. It's because omega 0 here is called omega 0. Omega 0 here is 0. You are, in the software, you can adjust omega 0 by this cursor, which is put set at 0 here. So red curve, cosine of omega 0 t. So omega 0 being 0, this is 1. And in the green sequence is cosine of omega 0 n. Yeah, you may not see the number here in blue, but it's 1, 2, 3, 4, 5, 0. Okay? And I'm going to increase omega 0 by moving this cursor. What do you see? You see a cosine function of small frequency value. You see it in continuous time and you see it in discrete time. But even by looking at the discrete time, you recognize the cosine. Let me increase omega 0 so you can see I increase the cursor. I increase omega 0, and what do you expect to see? You expect to see sinusoids that go faster and faster, that oscillate faster and faster. All right. Now, if you look at the discrete time, you still recognize the sinusoid. That means even if you didn't see the red curve, you would guess it from the sequence. Okay, so it keeps on increasing. Hey, look at this. This corresponds to pi over 2. Now you can see, you can have guessed that this is pi over 2, because this is cosine of 0, cosine of pi over 2, cosine of pi, which is minus 1, cosine of 3 pi over 2, which is 0, and cosine of 2 pi. All right. Anyway, you see the sinusoid. Now, if you just see this discrete time sequence, you wouldn't know it's from a sinusoid or a triangular function. Now, if you are told it's a sinusoid, then you know it's cosine of pi over 2n. Let me continue increasing. All right, let's continue. It's becoming hard to see a sinusoid, right? It's going to be really difficult to see the sinusoid, but the red line reminds you where the sinusoid is. Now it's really difficult to see sinusoid. Oh, this is funny here. Oh, look. Looks like it looks like the bones of a fish, a longer fish. What's that? Pi. Cosine of pi n. Is it surprise? So cosine of pi n is the same thing as -1 to the power of n. So if you plot this, you get a sequence like that. Now, all right. All right, so now I have a question. So you see this sequence. You see how it oscillates. Now I have a question. Is it possible to make a sequence that oscillates faster than that? Okay, is it possible to make a sequence that oscillates faster than that? Okay, 12, 13 answers. 14, 15, 16, 17, 18, 19. Okay, 20. Oh, wow. Wow, I have almost a 50-50 yes and no. All right. Okay. So for those who say yes, I'll try to make it for you. I'll try to make it for you. All right. I'm going to try to make a sequence that oscillates faster than this. You remember the majority wins. You win when the majority wins. So I'm trying to make you win. All right. So this is. Let me try to make a sequence that oscillates faster than this. Let me try. Let me try. Oh yes, I see. I can do it. Look. Yes, it oscillates faster. You agree? You agree? It oscillates faster. Yeah, it oscillates faster. Look. Yeah, I agree. So those who said yes, here's the result. I make it faster. So somebody said I got shot. Is it, how come? Yes, that's right. Okay. There is no way to make a sequence oscillate faster faster than -1 to the power of n. If you try, you. But I have another question. Another question. Do we get shot if we consider cosine of omega naught n with omega naught larger than pi? Okay, 7 answered. 9. 14. 15. 17. 19. One more. All right. Oh, so 7 students said you get shot if you take omega naught larger than pi. Okay, so I'm going to sacrifice myself. I'm going to see if I get shot. I'm going to get back to my software. So here, so remember, on top you have cosine of omega naught t. All right, so cosine of omega naught t, you can take any omega naught, right? And then in green, I'm going to take cosine of omega naught n. Now omega naught is already equal to pi. So I'm going to increase beyond pi. All right, I'm going to increase omega naught beyond pi. And according to 7 of you, I'm going to get shot. I'm not sure how it's going to happen. Maybe the computer is going to explode at my face and I will die, something like that. Right? So I'm a bit scared, but I will do it. All right. And if I die, then it's the end of the semester. No final exam. Too bad for you who wants to catch up. All right. So okay, I'm going to. All right. Yes. Thank you. Okay. If I don't see you again, I say you goodbye right now. But let me increase. Okay. I'm going to click. Ah, I'm still alive. I'm still alive. Now, did you see the red curve is still, look, the red curve, observe the red curve. It does oscillate faster, right? It does oscillate faster. Now, cosine omega naught n is still calculated normally. Now, there's no cheating. It's oscillating faster, right? And then, okay, now the green, I no longer know what's happening to the green. Let's continue. Look, what's happening to the green? So the red curve, it goes faster and faster. Let me continue. Hey, look at the green. It's a slow sinusoid. It's even slower. The green curve, the red curve goes faster, and the green curve goes more slowly, and now it goes back to zero frequency. Is that a surprise? No, we knew it would happen. We knew that was going to happen. All right. So we get back what we saw is that this becomes equal, but this is still much faster. But when you resample, it becomes equal. So physically, the conclusion is that physically, Pi is the maximum frequency. Is the maximum frequency. But you can still sample at higher frequency. You are not going to get a sequence like that. You're going to get a sequence that goes much more slowly. Now, I have another question. Can somebody tell me an example of this phenomenon in real life? Can somebody give me an example of this type of phenomenon in real life? Challenging question. Something that goes slowly when you expect it to go faster. Hey, give me this example, and then I will let you go. Time during a boring movie. Close to that. NTA. Train. All right, you are not it. You are not getting it. Yeah, I think you are okay. I give you no, real. I mean something concrete, something concrete. Okay, I think you don't have enough prerequisite in watching TV. No, not commercials. Not commercials. Not commercials. You okay? You want to have to watch enough of thrillers, police stories with helicopters. With helicopters. You know when you see a helicopter, yeah, helicopter blades, the propeller, the blades of the helicopter. Yes, in these movies you see the helicopter flying with the blades, the propeller that seems to rotate not very fast. Well, and it's not the helicopter is flying, but the blades, they seem to go slowly. That's exactly it. It's not an illusion. It's just the fact that a movie is not a real movie. It's a sequence. A movie is a sequence of images. Did you know that? It's a discrete sequence of images. So that's exactly the same thing. FPS, frame per second. It's frame per second. You're just saying that movie is a sequence of images. So this is exactly the same phenomenon. All right. So chapter 3, as you can see, is much more physical than compared to the other 2 chapters. Okay. You have to have a sense of what happens physically. It's not just pure algebra. It has more physical content, and this is often the reason why the final exam is the hardest exam among the 3 exams, is because you need to have some physical intuition of what's happening, physical intuition. Right? Okay, this is the end of the lecture. Bye-bye. See you on Monday.